Hello my dear friends, hoping that you are all fine with the blessings of Almighty Allah. Here we are right now starting the paper 6 variant 1, October-November 2020. So let's continue. And here first of all, question number 1 is: a student determines the density of modeling clay by two methods. Method 1, figure shows one face of a piece of modeling clay that the student uses. This is sample A. So the student measures the depth D of the sample, that is 3.2 centimeters. Now measure and record the length L and width W of the sample A of modeling clay. Figure 1.1 is drawn. Actual size. So we will make use of the ruler right now to measure this distance, measure these lengths. So L, it means we are supposed to measure from here till here, means including the arrowhead. So the distance comes to us, that is 3.1 centimeters. So these are rough values. They might be different from the values in the mark scheme, so no need to worry about that. We are in practice, just we need to know, or we are just in practice, so answers may be different from the answers in the mark scheme. So then W, similar way we are measuring, and that is equal to W will be also, we need to measure from arrowhead to the arrowhead, and arrowhead is included. That is to be 2.7, and centimeter is already written. And good thing about this paper 6 is that always formula or the equation is given, rule is given. Calculate the volume VA of sample A using equation L times W times T. So VA will be equal to 3.1 times 2.7 times 3.2. As we simplify them all, we are getting the answer roughly equal to 26.78. 26.78. So we can round it off to 26.8, and unit is given centimeter cube. Then my dear friends, next is figure 1.2 shows sample A on the balance. Record the mass MA of the sample to the nearest gram. Right now in this scenario it is to nearest grams, but also the examiner is asking in exams to the nearest 0.1 grams. So then we will be, right now answer is 51 and gram is written already. But if the examiner has asked you to write the answer to the nearest 0.1 grams, then it will be 50.8 grams. And I'm sure these things are clear to you till now. So we got the mass also, and the next now we are supposed to calculate, of course, the density. And again the rule for density is given. Calculate the density rho A of the sample A of the modeling clay using the equation rho A is equal to MA over VA. So all the values are with us. Give your answer to a suitable number of significant figures for this method and include the unit. So it is 51 grams over volume, which is 26.8 that we have calculated. So over 26.8 centimeter cube, and as we simplify we are getting the answer 51 divided by 26.8, it is equal to 1.902. So we can write it 1.90. So 1.90 grams per centimeter cube. This is one way to find the density. Then, my dear friend, the next is the student records. The method 2 is now adopted by the student. He is using a measuring cylinder instead of finding the dimensions of the clay. Record the volume V1 of the water using the measuring cylinder, and the answer is 150 centimeter cube. He carefully lowers sample B of the same modeling clay into the measuring cylinder until it is completely covered with water. So he records the new reading V2 of the water level in the measuring cylinder, and answer is 182. Now calculate the volume Vb of the sample B using the equation Vb is equal to V2 minus V1. So answer will be equal to 182 minus 150, it will be equal to 32. So 32 centimeter cube. The student measures the mass MB of the sample, that is 60 grams, and then again we are supposed to calculate the density rho B by using the equation, so which is equal to 60 over volume is 32. So this implies that 60 divided by 32, we are getting 1.875. We are not going to write this much number of significant figures. We can write 1.88 grams per centimeter cube. Now a student suggests that the density of the modeling clay is not affected by the mass or the volume of the sample used. State whether your results agree with the suggestion. Justify your answer by reference to the results. Justify your answers by the reference to the results. Now see, my dear friends, here the mass is 60 grams, volume 32, and in previous case mass is 51 gram and volume is 26.8. So they are not same, but the answers are almost same. 1.88 and 1.90 are almost equal. So in this statement, as usual, we are writing either yes or no. So in this case, yes, and they are very close. So either you can write they are very close, or you can write the conventional answer that within the limit of experimental accuracy. Within the limit of experimental accuracy means if we are trying to find the percentage error in these two results, 1.88 and 1.90 grams per centimeter cube, it will be less than 10%. So whenever the percentage error or uncertainty is less than 10%, it means the statement is yes and it is correct within the limit of experimental accuracy. Then tick the boxes that describes the correct lines of sight for taking a reading of the volume of water in a measuring cylinder. Figure 1.3 shows the curved surface of water, which is called the meniscus. Curved surface of the water is meniscus, and we are always measuring from the bottom of the meniscus, and also line of sight is perpendicular to the scale reading of the measuring cylinder. So 2 points are needed for accurate measurement with the help of measuring cylinder. So first of all, see along the scale, parallel to the scale, no, perpendicular to the scale. Like here, if I'm trying to do it, my dear friends, it will be something like this, perpendicular to the scale and also to the lower level of the meniscus, in line with the bottom of the meniscus. So these are the 2 points which we are ticking, and they are required to measure the volume of any liquid or irregular shaped object by making use of what? Measuring cylinder. Now my dear friends, let's move to the question number 2, that is about the thermal physics. And in our usual question, a student investigates the cooling of water under different conditions. Figure 2.1 shows the apparatus she uses. The thermometer in figure 2.2 shows the room temperature theta R at the beginning of the experiment, record theta R. So we need to measure this temperature 20 and 1 degree ahead, so 21 degree. If we are writing only 21, we are getting 0 mark. We need to write definitely degree Celsius, which is the unit of temperature, by liquid in glass thermometer, and you can check it by reading the theory or by looking at the diagram, and it is mentioned in degree Celsius as I circled on thermometer. So let's move forward. Now the student pours 200 centimeter cube of hot water into the beaker. She records the temperature theta of the hot water at time t is equal to 0. Then she immediately starts a stop clock after 180 seconds. Starting point is 0, and after 180 seconds she measures the temperature theta shown on the thermometer. Her temperature readings are shown in the table. So complete the time column and column headings in table 2.1. Time is in seconds, temperature is in degrees Celsius, and column headings here, it starts from 0 and then final value he is taking at 180 seconds. So these things are mentioned here, this one and this one. Then calculate the drop in temperature delta theta 1 between the time t is equal to 0 and t is equal to 180. So this is equal to 85 minus 69. As we simplify, 15 minus 9, 6, and 7 minus, so it is 16, but don't forget to write degree Celsius. Then calculate the average rate of cooling R1 of the water using the equation. See, again the rule is given, formula is given, and include delta T is 180 second, include the unit V value. So R1 is equal to delta theta 1, which is 16 degrees Celsius, over delta T, which is 180 seconds. So one thing is clear, unit is degree Celsius per second. What is the answer? 16 divided by 180, it is 0.0888, 0.0888, so on. So I can write 0.089. Then the student is repeating the same thing with some different measurements. The student empties the beaker. She pours 150 centimeter cube of hot water into the beaker, and then also she is adding 50 centimeter cube of cold water to the beaker. She repeats the timing and temperature recordings procedure described in B. The temperature readings are shown in the table. We can see them here. And again, complete the time column and column headings in table 2.2. Time is in seconds and temperature is in degrees Celsius. Again, this is 0 and 180. Calculate the drop in temperature delta theta 2 between the time t is equal to 0 and 180 again. So delta theta 2 is equal to 69 minus 57, 9 minus 7, 2, 6 minus 5, 1. So it means now it is 12 degrees Celsius. Now during this time now, the temperature fall is decreased when cold water is added. Calculate the average rate of cooling R2 of the water using the, again, rule is given. Delta T is 180, include the unit. So R2 is equal to, my dear friends, 12 degrees Celsius over 180 seconds. So 12 divided by 180, it is equal to 0.0666, 0.0666. So we can write 0.067 degrees Celsius per second. Then, my dear friends, now he is saying a student suggests that the average rate of cooling R of water depends on the difference of temperature, difference D between the temperature of the water at T is equal to 0 mean initial temperature and the room temperature. So calculate the difference D1 using the readings in table 2.1 and your answer to A. Answer to A is the room temperature, which was 21 degrees Celsius. So D1 is 85 minus 21, that is equal to 64. So it is 64 degrees Celsius. And similarly calculate the difference D2 using the readings in table 2.2 and your answer to A. So that is my dear friends 69. D2 is 69 minus 21, so 8 and 48 degrees Celsius. Write a conclusion about the relationship between R and D. Justify your answer by reference to the result. Conclusion is, I am writing in shortcut that rate of cooling, which is R, is directly proportional to the difference between the temperature of the hot water and the room temperature. So I did not use the theory, I have just written it with the symbols. You should write your theory. So what should you write? Rate of cooling of the water is proportional to the difference between the temperature of water, initial temperature of the water and room temperature. Now justification. Justification, you can say that for D1, R1 is equal to 0.089 degrees Celsius per second. From where I am getting, see, this is D1 when initial temperature is 85. So R1 is 0.089 degrees Celsius. And when this difference of temperature is D2, R2 is equal to 0.069 degrees Celsius per second. So when difference of temperature is low, the rate of cooling is also low. Difference of temperature between what? Difference of temperature between the initial temperature of water, in other words, in this case hot water, and the room temperature. When it is less, rate of cooling is less, and when it is more, rate of cooling is also what? More. Explain why thermometer scale should be read at right angles. So when we are doing so, it means we are avoiding the parallax error. To avoid parallax error, and then explain why the mixture of hot water and cold water should be stirred before taking the temperature reading at the start of the experiment, and see when you will be stirring it continuously before taking the temperature reading, it means the temperature will be uniform, the reading of the temperature will be uniform throughout the liquid. It is done to get constant temperature, throughout the liquid. Yes, my dear friends, so that you will be continuously stirring to get even temperature or uniform temperature throughout the liquid. Stay blessed, my dear friends. If you have any question, any particular past year exam question or part of the question, please share me on this YouTube, and I will be trying to respond that question as soon as possible and sharing the video here on the YouTube channel. And if you are thinking that these things are useful for you, these explanations are useful for you, so please share my channel with your friends, family and friends, and do subscribe it. Thank you. Bye.